Okay, so today we're going to review Unit 2, Symbols Say What. And this was a unit that was pretty big, and we had split it into two different units. So bear with me here. Make sure you read through the standards and the topics, and you make note of what you don't remember so you know where to focus your study. If we go into the review, a proton is positive, has a relative mass of 1, and it is found in the nucleus. The electron is negative. It has a relative mass of 0, and it's found in the electron cloud. The neutron is neutral. It has a mass of 1, and it is found in the nucleus. So if you look, only things that are in the nucleus have mass. So the nucleus contains most of the mass of the atom. Isotopes are the same element, but they have different masses because they have different neutrons. So they differ in the number of neutrons, not protons. Remember, protons have to be the same because that's the atomic number and that indicates the element. So if we look at our AZX formula here, Z would represent the atomic number, or the number of protons, and A would be the mass number, or the number of protons plus neutrons. So then if we look at our example here, 20F, the atomic number, we'd have to go to the periodic table, and we can see that the atomic number of fluorine is 9. So if there's nothing written in the bottom, then you can just look on the periodic table. The mass number is not on the periodic table. That is found in the upper right hand or upper left hand corner. Remember, the other way that they can write this symbol for us is by writing the mass number after the dash. So like F-20. All right, so then we're going to fill out our chart here. Uranium on the periodic table is 92. So it has an atomic number of 92, which means it has 92 protons. There is nothing in the upper right hand corner, which means it is neutral. So the number of protons has to equal the number of electrons. The mass number in the upper left-hand corner is 238. So then to find the neutrons, we're going to take our mass number, 238, and minus our protons, 92. So 238 minus 92 gives us 146. For oxygen here, oxygen on the periodic table is element number 8. So it has the atomic number 8, so it has 8 protons. Now look, the charge is -2. Remember, negative charge means they've gained 2 more negative electrons. So instead of having 8, it now has 10. The mass number is given to us in the upper left-hand corner, so 16. And so to find the neutrons, we take our mass number minus our protons to get our neutrons. And then finally, sodium is number 11 on the periodic table. So it has 11 protons. There's a charge of +1. And remember, a positive charge means you lost 1 electron. So there's 10. The mass number in the upper left-hand corner is 23. And so for our neutrons, we would say 23 minus 11. And so we have 12 neutrons. Energy level, remember the symbol is N, and we can look at the Bohr's model on page 8 to remember that. The larger the energy level, the farther away it is from the nucleus. And then if we use the periodic table, the highest occupied energy level corresponds to the row or the period on the periodic table. And remember, rows and periods go horizontally across, and there are 7 periods and 7 rows. So if we look at the periodic table and we find bromine, we'll see that bromine is in the 4th period or the 4th row, so it has 4 energy levels. Oxygen is in the 2nd period, so it has 2 energy levels. So the row or the period tells you how many energy levels there are. Just some definitions here. Ground state is low energy. Excited state is higher energy. Right. Hydrogen line emission spectrum. is emitted as the electrons fall from an excited state to a ground state, and they release a photon of energy. And sometimes that energy we can see as light. Now, I would highlight or star number 6. This is definitely going to show up on the midterm, and a lot of you missed that on your test. Okay, so for number 7, we're looking at Bohr's model on the back of our reference tables, page 8. We're going from the third energy level to the second energy level. So we want the dot to be on the third energy level, and it needs to be pointed to the second energy level. If we trace that back, we get a wavelength of 656. Now that's in nanometers. So if we convert that to meters, we would put the decimal between the first 2 digits and then just tack on times 10 to the negative 7 meters. We can then look at the bottom of page 8 and see where 6.56 times 10 to the 7th falls in our number line, and it falls just over the red, or into the red. So this is a red color. The type of electromagnetic radiation would be visible. Remember, wavelength is a number, then we have the color, and then we have the type. All right, then we looked at nuclear chemistry as well. So alpha, remember, looks like a fish. I can't draw that on the computer here. Beta is a bee with a tail, and then gamma looks like a scripty Y. The charge, or if we wanted to see it in a notation, as in like what it looks like in a reaction, for alpha, it would be 4 over 2 He. Beta would be 0 over negative 1, which makes it an electron, and that's a lowercase. And then gamma, we don't see because it's just energy. The charge of the alpha is +2 because of the positive 2 protons there. The beta particle is -1. Gamma, again, is nothing because it is just energy. The mass of alpha is 4 because it's 2 protons and 2 neutrons. Beta is 0 because it's an electron. Gamma, again, Na, because it's just energy. Alpha, having the largest mass and the largest charge, is the weakest. Beta is still considered weak. And then gamma, being just energy, is very strong. So to block alpha, we can just use something as thin as a piece of paper. Beta, we need something a little bit thicker, maybe a piece of wood or a piece of metal. Gamma, we would need 18-inch thick lead. So it's really hard to protect yourself from gamma. All right, fission, division. So one nucleus breaks into 2 lighter, stable nuclei. And then fusion, you're bringing 2 things together. So 2 lighter nuclei combine into 1 heavy nucleus. Balancing the reactions, remember the law of conservation of mass. So we would just say 37 plus 1 equals, all you have to do is treat that arrow as an equal sign. So that would be 38. And then for the bottom, 17 plus 1 would be 18. And then we would look on the periodic table. And number 18 is argon. Remember, it is the atomic number that is telling you what the element is. All right, I'm not going to do B and C just for time purposes. Half-life is the time it takes for half the amount of a radioactive substance to decay. So for this one problem, you have a half-life of 90 seconds. There's 1 million atoms prepared. How many atoms would remain after 4.5 seconds? Okay, so we would take our 2 time values, 4.5, we would divide by 0.9. That tells us there were 5 half-lives. And then we're going to take our million atoms, divide it by 2, and we get 50,000. And then we're going to divide that by 2 again. And then divide it by 2 again. And then by 2 again. So that's 1, 2, 3, 4, 4 times. So we need to do it one more time. And our final answer then would be 12500. And so that is our answer. All right, a period is the same thing as a row. It's horizontal on the periodic table. Groups are the same thing as families. They're the columns, but we don't call them columns. They're vertical on the periodic table. The periodic law states that elements in the same group have similar properties because they have the same number of valence electrons, and therefore they have the same charge. All right, reactivity, metals are more reactive closer to francium. Nonmetals are more reactive closer to fluorine. The group that is non-reactive or inert is the noble gases, which is group 18. Metals are found to the left of the stairs. Metals always lose electrons. When you lose an electron, you form a positive ion. We call that a cation. Metals are malleable, ductile, they have luster, and they conduct when solid. Nonmetals are found to the right of the stairs. They gain electrons. They form negative ions, which we call anions. And they are non-conductors, so they don't conduct electricity, so we call them insulators. Metalloids are found along the stairs. But remember, not aluminum. Even though aluminum touches the stairs, it's not a metalloid. Aluminum is just a regular metal. You can list out those elements by looking at the periodic table. The one property that you need to know is that they are semiconductors. Representative elements or main group elements are located in groups 1 and 2, and then 13 through 18. So these are our A groups. Alkali metals are group 1. They will lose 1 electron, so they form a +1 charge. The properties that you need to know is that they are the most reactive metals. They're so reactive they're not found pure in nature, but they are found in stable compounds. Alkaline earth metals are group 2. They lose electrons because they're metals, and metals always lose electrons. And when you lose 2 electrons, you form a +2 charge. Transition metals are groups 3 through 12. They will lose electrons because they are metals, but their charge is going to vary. We have to be told what it is. And that's the property that you need to know about transition metals, is that they can form more than one charge. And each charge has a color associated with it. Don't worry about E. We haven't done naming yet, so you can just kind of ignore that part. Halogens are group 17. Those are nonmetals, and nonmetals will gain electrons. And group 17 has 7 valence electrons, so they're going to gain 1 electron to form a -1 charge. For properties, they are the most reactive nonmetals. Noble gases are group 18. They do neither gain nor lose because they're already stable. which is what their big property is. They're stable, they're non-reactive, and remember that fancy word, inert, for non-reactive. All right, and then we have our different areas on the periodic table. So you have the S block, which is groups 1, 2, and helium, because remember helium finishes out that first row. All right, the P block is groups 13 through 18. The D block is groups 3 through 12. And then the F block are the bottom 2 rows. I can't do orbital notation on the computer. Just remember that those are the lines and the arrows, and that the lines represent the orbitals. The arrows represent the electrons. The large numbers represent the energy levels, and then the letters represent the sublevel. If we wanted to do electron configuration, we would say 1s2, and we can just read the periodic table to do this. The second row, S block, 2 elements, keep going across. Still on the second row, P block, there are 6 elements, and we're at neon. Moving down to the third row, 3s2 puts us at magnesium. 3p6 would put us at argon. And then we have 4s2 to get to calcium. Remember, when you get into the D block, it goes down by 1 for the row. So this would be 3D, and then we'll count all of those to zinc is 10. And then we're back to the fourth row in the P block, and bromine is the 5th one. So when we do the noble gas notation, we're taking that and shortening it even more. So the noble gas that comes before bromine would be argon. So argon finishes out row 3. So we can just put argon in brackets, and then we can take away all of this part because that's what saying argon in brackets represents. And then we just have to tack on the row that bromine's on. So 4s2 gets us to calcium, 3d10 gets us to zinc, and then 4p5 puts us at bromine. Number 29, looking at these and trying to figure out the element, you could add up all the exponents if you wanted, 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 6. Or you can look at the fourth row and go across 4s2 and then 3d and count to the 6th element, and you would be iron, which is Fe. It would have 2 valence electrons. Because remember, those are the outermost electrons, and the 4th energy level would be the outermost electron, and there's 2 electrons there, or outermost energy level. And it will lose electrons, but how many it loses will vary because it's a transition metal. All right, 3s2, 3p4, so third row, go over 3s2, and then 3p4, count over 4 in your sulfur, which is S. It's in group 16, so it has 6 valence electrons. And so it's going to gain 2 more electrons to form the charge of 2 minus. All right, I can't put the roadmap on the computer, but remember mole is in the middle, and then you can go to grams, which is your molar mass, or you can go to liters, which is 22.4, which is found on page 1 of your reference table, or you could go to IPAM, which is also Avogadro's number on page 1 of your reference tables. So then there's some examples here. For A, we know that this is 1 step, and we know this is 1 step because mole is in the problem. So if we were to set up our table, we would set it up for 1 step. Remember, you always start with the given. So you just have to pretend this border here is not actually there, and then it would look like a table. And then you take whatever the unit and substance is and you bring it diagonally down to the bottom. When you're at mole, you're at the center, so you can go anywhere. And on top, we're going to put molecules because that's where we want to go. 1 always goes with mole. Molecules would be Avogadro's number, and remember that's on page 1 of your reference table. And then that's it, because moles would cancel. Let me move this over so I have space to give an answer. Numbers next to each other, you multiply, top and bottom you divide. So you would say 4, where's my calculator? So you would say 4 times 6.022 special button 23 divided by 1. We want 3 significant figures because that's how many are in our given. And we would get 2.41 times 10 to the 24th molecules of CuCN2. Then if we look at number 2 or letter B, this would be 2 steps because mole is not in the problem. So this one would be a little bit longer because you have to go through mole to get to your answer. You're still going to start with your given. So we're going to start with 24 grams of FeF3. We're going to bring whatever that unit and substance is diagonally down to the bottom. And then if you don't have mole on the bottom, you have to put mole on the top. So we're going to put mole FeF3 on the top. 1 always goes with mole. And then with mass, we put our molar mass. So then we look on the periodic table and we add the mass of iron plus the mass of 3 fluorine. So iron plus 3 fluorines would give us a mass of 112.85 grams. We're trying to get to molecules, so we're going to keep going. We're going to bring mole Fe3 down to the bottom. Remember, 1 always goes with mole here, and we're trying to get to molecules, so we're going to go to molecules on top. Remember, Avogadro's number goes with molecules, so 6.022 times 10 to the 23rd, just like it's written on the front of your reference tables. And then we can get our answer. So we're going to multiply and divide away. So we would say 24 divided by 112.85 times 6.022 special button 23. We want 2 significant figures this time, so we would say 1.3. And then don't forget to look at that times 10 at the end of the number. And we would have times 10 to the 23rd molecules of FeF3. All right, I'm not going to do the other 2 problems. They're very similar to these 2. All right, atomic radius, the definition is the size of the atom. The element with the greatest atomic radius is francium. The element with the smallest is fluorine. The reason, as you move down a group, you are gaining energy levels. So to put the following in order of size, we're going to say it is, we would say potassium, calcium, then copper, and then finally selenium. Ionic radius is the size of the ion. Cations, remember, are atoms that have lost electrons. They form positive charges. Anions are atoms that have gained electrons. They have negative charges. Okay, cations are smaller because you've lost the electrons. Anions are larger because you've gained them. Metallic activity, the definition would just be how metal-like it is, how easily it loses electrons. So it increases towards francium. The least metallic group then is group 18. Metals have low ionization energy and low electronegativity. Ionization energy is the energy needed to remove an electron. Highest ionization energy would be helium. Lowest ionization energy is francium, and that's because the larger the atom, there's less attraction between the nucleus and the valence electrons. So putting these in order from the lowest to the highest ionization energy, we would say Bi, Sb, P, and then finally N. Electronegativity or electron affinity is the ability for the atom to gain electrons. Highest electronegativity is fluorine. Remember, we don't count group 18 because they'll never gain electrons. Lowest would be francium. The smaller the atom, the stronger the attraction between the nucleus and the valence electrons. So putting these in order of lowest to highest, we would say Ra, Ca, Mg, and then Be. All right, try the rest of the problems on your own.